In this video, we're going to do a few more examples of VSEPR theory. I just want to point out before we do those examples from your notes that you're allowed to use your VSEPR table on your assessments, and you can find it under the regular day calendar. The VSEPR table is right over here. This is what you're allowed to use. So do have it with you when you're doing practice problems, so that way you understand how to use it and you become very efficient with using it. So let's go to our examples here that we were doing. I'll be doing the Lewis structures fairly quickly, and then we're going to be figuring out the shapes from the Lewis structures. So we'll do SO3. We did SO3 as an example in our Lewis structure notes, but essentially we saw with formal charges, it was best to have these double bonds there. So 3 double bonds were written out. And we have a central atom, which is A, and we have 3 atoms that surround it. So it's X3, and there's no lone pairs. So we have AX3. And so that's over here. No lone pairs. It's essentially this over here, everything in the plane. The electron geometry is trigonal planar, and so our molecular shape is trigonal planar as well, with bond angles of 120 degrees. And so we can go ahead and write that out as our shape, molecular shape, trigonal planar. We have a 120 degree bond angle. And we can draw it out like this, more spaced out than our Lewis structure. And there are lone pairs. We can now try CCl4. We have our central atom is carbon, surrounded by chlorines all around. We don't have any lone pairs around carbon, but we do have our shared pairs. We have our 4 peripheral atoms, so we have an AX4 molecule. And if you look at your VSEPR chart, the AX4 molecule is right here, 4 regions. And if you look at that, let's erase this so we can see what's happening here. It's a 3D shape where we have some bonds coming out, some bonds going behind, and then some on the plane. And that's a tetrahedral electron arrangement, and therefore a tetrahedral electron shape with 109.5 degree bond angles, since we don't have any lone pairs there. So we have the tetrahedral arrangement for CCl4. So that's our molecular shape, tetrahedral. So like this, with our CLs in the plane. I'm putting my lone pairs there, hard to see. There they are. CL over here. And then some CL popping out at us with our wedge. And then some CL going behind the screen with our dashed line. And again, this bond angle between the atoms is 109.5 degrees all around. Let's try another example. We'll do the O2 molecule. And so when you do O2, you'll get something like this, double bonded O's with our 2 lone pairs like this here. And so this is a bit of a weird one. We don't really have a central atom. It's just 2 atoms connected together. So in a way, we just really have sort of an AX type of molecule like that. And so you can also look at it as a, you can look at it from the perspective of many of these molecules that are linear. So you might see, for example, might resemble something like this as well, except we don't have the 3 lone pairs. So we're really looking at something that's more of an AX type of molecule. You might even say it could be an AX E2 type of molecule as well. But at the end of the day, they're all going to be the same arrangement, which is a linear shape of molecule. Theoretically, there's no bond angle. So we'll call this AX. And the reason I'm saying there's no bond angle is because usually a bond angle is measured between atoms. Let's call this atom an atom here, atoms around a central atom, and this would be a bond angle. These don't really have that. So if you only have 2 atoms, you don't officially have a real bond angle. The shape is still considered linear because it's a straight line. So if we were to draw that, we just draw it in the plane like this, just as we normally would, with our double bond in the plane. And we'll say that the bond angle is about 180 degrees, even though technically, because it's 2 atoms, there are no bond angles. So if someone ever asks, what's the bond angle here? We could say, well, it's linear, so it's like 180 degrees if you were to measure from somewhere. But in reality, by definition, there is no bond angle there. And let's finish off this video with our last example of O3. We'll do the PO4 example in another video. So we have O3 here. And when we're drawing O3, we have a central atom, which is O there. We connect our O's to the other ones there. And I just want to show you this one because it's quite interesting. When you do ozone, you basically have 6 times 3. That's 18 electrons a place. And so when you place the 2 bonds there, you've placed 4 electrons, and that's 14 left to place. And so you'll get essentially your 6 electrons around each oxygen, and then that there as well. And so theoretically, you might say, well, this looks okay. We've run out of electrons at this point, so we're happy, but we're not, because this oxygen in the middle doesn't quite have its full octet. So we need to borrow from here to make a double bond there. And you could have borrowed from any oxygen overall to make that double bond. It could have been the other oxygen, which leads to VSEPR shapes, or which leads to resonance structures rather. But in the case of just looking for a shape, we can just draw one of the structures, and that should suffice to help us find what our overall shape is in the end. So we have one double bond there. And again, typically I'd ask you to draw a resonance, but since we're just looking for the shape, it's no big deal. We have a central atom and 2 peripheral atoms. So we have an AX2, but then we also have a lone pair. So we have an AX2E1, or E, as we would call it, AX2E. So it's 3 electron regions, really, but one of them has been plopped off and replaced by an electron, so by an electron pair. So if we go here, what we're looking at is 3 electron regions, almost like an AX3, but one of the X's was replaced by an E. And so typically the AX3 would be 120 degrees, but because now we have a lone pair, that has more repelling effect, so it reduces the angle to less than 120 degrees. So yes, we have a trigonal planar electron geometry with the way the electrons are distributed throughout. So this is the electron geometry that you'll see over here between the electrons themselves. But overall, the atom, the atomic shape between the X and the X will make a bent molecule with less than 120 degrees. So we have an AX2E1. The molecular shape is bent. And so we can draw it like this. We have our lone pairs there. Our peripheral atoms like that. And this angle here is less than 120 degrees, as opposed to 120 degrees that you would see in a trigonal planar molecule with all the electrons in bonded pairs rather than a lone pair up there. And so that was some more examples of using VSEPR theory to predict the molecular shape and bond angles. In the next video, we're going to do one more example with the phosphate ion. But again, I always encourage you to try it yourself and then to check the video to see if you were on the right track with the concept.